So we mentioned a couple concepts in the last section that we're going to return to and expand on here. The first one was that we left off talking about the magnification of an extended object, and the second one is the concept of a real image versus a virtual image. So I promised you that we would see an example of a real image if you couldn't imagine what I was talking about with the rays crossing through the actual image that's formed. So I kind of mentioned this before. If you've ever been to a carnival or a county fair or something and been in just like a weird house of mirrors, you've seen yourself in wacky mirrors where different parts of your body look distorted. And this is, of course, because the mirrors are not just flat, plain mirrors, but rather some creative manifold surface. The radius of curvature of each point on the mirror determines how the light reflects and where it will form an image that your brain sees. And so we're going to analyze the simplified case of just a spherical mirror, and this will help you understand the behavior of light as it reflects off of any curved surface, no matter how complex, because we're going to be left with a couple equations that will help you determine that. So, if you consider a spherical mirror of radius r, the center of curvature, which is the center of the circle of which the mirror surface is a part of, at point C, and the vertex, which is the center of the mirror surface, at point V. So let me draw all this. So we have a mirror, but it's going to be a spherical mirror, the best I can draw anyway, like that. And we have the center of curvature, C. This would just be that if you were to complete this circle, that would be the center of the circle, right? And then we have a vertex, V, which is just at the center, right? So there's the same distance going on there as there is there. And that's usually defines the optical axis, which would be the line through those two. And so that leaves this distance here, from here to be the radius of that circle, right? So let's take the case for a point object P residing to the left of the center of curvature. So I'll use this same image though. And we're going to take a point object that lies over here, P, to the left of the center of curvature. Where will the image be formed? So I assert to you that the image will be formed here, because I'm telling you so, but we're going to prove it later. So let me draw the rays just so you can imagine it. So coming from the object straight through the center of curvature, hitting the vertex, which isn't drawn perfectly. It's coming out like that, and it's coming back, and it intersects with that that image point that I've asserted. So far so good. And let's see if just visually or geometrically any of this would be convincing to you. So if you have a bunch of rays coming out, just like we did with the plane mirror, draw one more up here. And you have the same ones going on down here. Okay. All right. They reflect according to the law of reflection. So at each of these, there's some normal to the mirror going on, and there's the incoming, and so they would reflect based on that same thing, so that the angle outgoing is the same. So if this is theta, that's also theta. And that's happening for each of these points. I'm going to just clean, too much. I'm going to clean it up just a little bit here. Fine. And draw the rest of them. And this is not supposed to be a mathematical proof for you, just kind of a geometric way to maybe convince you for now before we go through the actual proving that this is the case. Oops, it's not very, there we go. Come on. one more. All right. So maybe by my imperfect spherical mirror drawing, you're not as convinced. Maybe because this image distance from the mirror isn't exactly where it physically would be, it doesn't look perfect, but I assert to you that we can prove that, my bad drawings aside, that the image point, the image would be formed somewhere between the center of curvature and the vertex. And that's generally what it would look like right there. So, before we move on into that proof, there's something very important to notice. So the image that's formed, P prime, is a real image, not a virtual image like with the plane mirror. In other words, the reflected rays actually do cross through the image point and continue on as if they emanated from this point, right? So this is the image that's formed right here, and there are actual rays that are crossing through that. And so if you were to erase everything and just look at rays emanating from this point, I'm just going to do it in green here, right? This ray is coming off of this point, as if this were its own object with rays emanating from that. It's kind of interesting. So what does that matter exactly? If you see the image just the same, whether it's a real image or a virtual image, what does that matter really? Well, this is what allows photography to work. Real images is the only way that cameras can pick up on images, because actually light has to cross where the image is formed for the film or the CCD to pick up what's going on in a clear image. So the actual light forms an image in the physical location that the film or CCD of a camera can be placed to capture the image. So if this doesn't make too much sense, imagine this. Imagine if our point object were the only source of light and it were in front of a plane mirror. So let's go back up to this guy here, right? This scenario. If you put your camera where the image is formed, which is behind the mirror, right? If you put your camera here, right at that virtual image point, your camera wouldn't capture anything because there's no actual light back there, right? There's no actual light back there. So with virtual images, the image cannot be captured by a camera or any device that relies on detecting photons to observe the image. Now trade that plane mirror out for a spherical mirror. To capture a clear image of the point object, you could just place your mirror at exactly, or your camera exactly here, where all of the rays converge at the actual image point, and you would get the image that's formed at point P on your camera. So this is the usefulness of real images as opposed to virtual ones, right? You might be thinking, well, what the heck, how do we see things or anything? And this can't always be the case. Well, I guess you could be right. If you had a large enough camera, right, super large camera, and you had some further optics going on where the rays converge, then converge back, right, and the CCD is back here somewhere, right, then I suppose, yes, you could capture it. But if you're just talking about putting a light-sensitive detector at the image point, you can't do that with a virtual image. You can only do that with a real image. So that's the usefulness of real images. You don't have to have all those fancy optics with ginormous lenses to reconverge all the diverging rays and whatnot. All right, so we're going to pause there, and then we're going to pick up in the next video with the proof that is where the image point is.